Sometimes when you're analyzing a circuit, you can reduce the capacitor bank or the resistor bank and figure out a way to reduce all of the resistors or capacitors to their equivalent value, and then you can solve the problem. However, not all circuits are reducible, so we're going to look today at the Kirchoff's rules. He has a loop rule and a junction rule, and these rules will always work in a circuit, so they are universal. We see that we can reduce this circuit at least somewhat. We see we have a couple of resistors, the 2 and the 4 ohm resistor, they're in series with one another, and the 5 and the 1 ohm resistor that are in series with one another. And even though they're both in parallel with the 3 ohm resistor, notice that there are 2 potential difference sources here, and they're on different parts of the circuit. So we can't just use the reduction, add the potential together. We need to evaluate the circuit. And so Kirchoff's loop rule says, as I work my way around from one side of the battery around any loop, could be the entire piece, what I will find is that the potential drops are equal to the potential rises. Now, we've already discussed this before when we were working our way around a battery, but this is Kirchoff's rule. We can also then do smaller sections. So here's a smaller section up there. Same thing, I add 24 volts. So by the time I go through all 3 of these resistors, I must have dropped 24 volts. I can do the same thing on the bottom loop. However, this particular picture has already picked the current directions for me, so I'm going to use these 2 loops as we evaluate them. The junction rule is a consequence of the conservation of charge. So if I have this junction labeled A, then the current that comes into A must also come out of A. Now here it's coming out in 2 pieces, and so the current in equals the current out. These 2 rules will allow us to design a system of equations, and from that system of equations we can solve this circuit and talk about the different parts of it. Okay, I'm going to start with the junction rule where we left off. And so if I'm looking at this junction right here, I see that coming in I have I1, exiting I have I2, and I have I3. The directions are given for me, and so I know what that looks like. I do actually have another junction over here, junction B. At junction B, I get I3 and I2 joining to give me I1, but that's actually the same equation that I already have, so I don't need to write it a second time. Now let's go to a loop, and so the first loop I drew was all the way around, so I'm going to start with that one, loop 1. Loop 1, I'm looking for rises, and those have to equal the drops. Right? I'm going to use Ohm's law here, V equals IR, that we've talked about before. So I'm just going to start here at the battery. This battery puts in 24 volts. I'm going to work my way around the loop, so the next thing I do is run across this 2 ohm resistor. So I have a 2 ohm resistor with current running through it, and that current is I1. So I1 times 2 ohms. Then I have a 4 ohm resistor that also has I1 running through it. So I can actually think about those in series and rewrite this as 6 ohms. I've got a 4 ohm resistor and a 2 ohm resistor in series with one another, so 6 ohms. If I keep going, I have a 1 ohm resistor and a 5 ohm resistor, and so through them is I2, and their combination is 6 ohms. I'm not quite done. I've got to come back around here. I have a negative to positive, so that's a rise. So I have a 12 volt rise, and then I'm back at my battery, so I put my equal sign in here. And so these resistors and these resistors together drop all of the potential that's put in by the circuit. So I can simplify this. I've got 24 and 12, but there's 36 volts. And then I've got these two over here. Now, I'm going to leave out the V's and the ohms since I'm writing this with variables in there. So I have 36 is 6I1 plus 6I2, and I see right away I can reduce that. So 6 is equal to I1 plus I2. All right, I've got a second loop there, so I'm going to go ahead and look at it. This is the one I called the second loop. And if I look at the rises, I have a 24 rise. I've got my same 2 resistors in series, so 6 ohms. So I1 times 6 ohms. And then my next drop is across the 3 ohm resistor, and it has I3 running through it. So 3 ohms there. So again, typically we're very picky about making sure units are there. We're going to simplify that for solving here. So we have 24 is equal to 6I1 plus 3I3, and I can simplify that. So 8 equals 2I1 plus I3. So I have these equations. I have I1 equals I2 plus I3. I have 6 equals I1 plus I2. And I have 8 equals 2I1 plus I3. 3 equations. I have 3 unknowns, so I ought to be able to set up this system and solve it. So we're really done with the physics portion. We just need to find a way to solve our system of equations. There are many ways to solve these systems of equations. I'm going to use, just take 3 equations and use some substitution. You're welcome to use any method that works and is valid. So I've got my 3 equations from the previous slide that I'm writing here. I see that I1 is in all 3 equations, where I2 and I3 are only in 2. And so I'm going to take this equation here in the middle, and I'm going to put I2 in terms of I1. So if I write I2 equals 6 minus I1, and I'm going to look at this third equation, and I'm going to put I3 in terms of I1. So in that case, I've got I3 is 8 minus 2I1. Now I can go to my first equation, and my first equation says I1 equals I2, which is 6 minus I1, plus I3, which is 8 minus 2I1. So now I've got a single equation with a single unknown. So I1, 14 minus 3I. So that gives me 4I1 is equal to 14. I1 then is 14 fourths. And that reduces to 7 halves. So we might write 3.5. Now again, I haven't been using the units throughout, but if I'd been consistent, I know that when I get to current, I ought to have amps. So I1 is equal to 3.5 amps. All right, so we know that I1 was equal to 3.5 amps. And if I1 is equal to 3.5 amps, then I2 equals 6 minus 3.5. That gives us 2.5 amps. And I3, that was 8 minus 2 times I1. And that ought to give us 1. And just like we expect, I1 is equal to I2 plus I3.